Hi guys, welcome to VLSF for all. In the Verilog series, I am representing the presentation of full subtractor and its implementation in Verilog using Xilinx ISC 14.7 version, using three types of abstractions like data flow modeling, behavioral modeling, and structural modeling. A full subtractor is a combinational circuit that performs subtraction of two bits, one is minuend and other is subtrahend, and also taking the borrow of previous adjacent lower minuend bit. This circuit has three inputs and two outputs. The three inputs A, B, and B denote the minuend, subtrahend, and previous borrow respectively, and there are two outputs, difference and borrow out. Here is the truth table of the full subtractor as shown in the figure. See here, A, B, and B are the inputs, and D and B out are the outputs obtained from the inputs. See, when their inputs are 0, 0, 0, then the difference is 0 and B out is also 0. When we take 0, 0, 1 as the input combination, 0 minus 0 is 0. 0 minus 1 will be, it produces a output difference 1 and with borrow 1. When we take input combination of 0, 1, 0, see here 0 minus 1 means 1 with borrow 1. So with that 1 minus 0 again I will get 1 and 1. 0 1 1, see 0 minus 1 means difference 1 and borrow 1, and again 1 minus 1, see 1 minus 1 will be 0, so difference will be 0 and b out will be 1. Like that these input combinations are tried for the rest of the inputs. See next we will see how the full subtractor is implemented by using logic gates. See there are three inputs and two outputs, difference and borrow out. Here uh, if you see carefully the structure of the circuit, it shows the circuit of the full half subtractor and it is another half subtractor. Means if you want to obtain the full subtractor, you have to couple both of the half subtractor circuits and with by using an OR gate. See like that we will get the borrowed output and difference outputs from the full subtractor. So we have to use two half subtractors, and this can be implemented by using structural modeling. Now let us see the truth table of the full subtractor, and we will derive the logical expressions from the full subtractor for difference and borrowed outputs. Let us see. Now see here, we are mapping from the difference and borrowed. See here, when we have to write the K-map, by using K-map we have to minimize the expression for difference and borrowed. See when they are ones, those values are to be noted and we have to minimize it using a K-map. See here, once when they are ones we have to note the values 1, 2, 3, and 7. For 1, 2, 4, and 7, the difference is high. So we are taking those inputs, and B out is 1, 2, 3, 7. And these for these inputs, the B out is high. So we have to use represent it using a K map. It is a three variable K map. So here for difference 1 and no grouping is possible here. So that I have written like this, and the output obtained when we minimize this will be AX or BX or B in. This is the output for the difference and the logical expression for difference. This is the expression for borrow out. See here, grouping is possible. So I got three groups. So X, A bar B in plus A bar B plus B into B in. So I got the expression for borrow out. Now let us go to coding part. See here, I have written as I have declared a module, and in that module, this is the full subtractor. So I have written full subtractor, and what are the inputs? A, B, B in are the inputs, and the outputs are D and B out. So I have written input and output. So as I am using data flow, but behavioral and structural modeling, I have written all the codes, but I have commented like that because we have to use any one of the modeling for the simulation. So in data flow modeling, see here, assign statement is used. Why data flow assign statement is used? Because it is a concurrent assignment statement which is only to be used in data flow modeling. So I have assigned D with AX or BX or B, which is obtained in the logical expression for the difference. So here also B out is equal to same expression I have used it here in data flow modeling. And in C, behavioral modeling, in this we have used a procedural block, means always block. Always block is a procedural block. So I have used star operator. Why star? Because it indicates the change of any of the input combinations, it will be activated. And when we use D and beyond, why we didn't use assign statement here? Because it is a procedural block, and procedural block does not have continuous assignment statements. So I have used it like this. And when we are using behavioral modeling, this D and beyond are to be declared as rich type variables here. Then only we will get the output, otherwise we will get an error. See here, structural modeling. When we see the structural modeling, we have to consider the structure of the gates. That means this. When using structural modeling, I have implemented and I have written Verilog code by using this, and I have written like this. So I am ending the module. I am simulating by using only data flow modeling. We can use both of the three of the modeling styles to get the output. And I have written the test bench like this. See, I have initiated and declared as inputs as the rich type variables and outputs as wires. And I have instantiated the design part under test bench so that we will get the inputs and outputs here. And I have used initial begin block, and I have written dollar monitor to display all the values of a in, b in, and everything, and outputs. And also I am giving inputs after every delay of 10 nanoseconds. Why 10 delay is produced provided? Otherwise we will not get output, because if we didn't have delay, then the input will be constantly same with the same. In the current zero simulation time only the output will be presented. But if you want for various input combinations, then you have to give some delay. So I have given a delay of 10 nanoseconds, and I have written the code. See here, after that, after a delay of 100 nanoseconds, I am finishing my code. I am finishing my simulation time, so that I have written like that. See now, let us see the RTL part of the, this is the RTL schematic we have obtained for the full subtractor. What are the inputs and these are the outputs. Now let us see the simulation waveform. See here, when the A and B, see here, wait, I'll crop. Now see, when the A, B and B in are both all are zeros, then the difference and the B out are also zeros. After that, see here, when 0, 0, 1, as we see in the truth table, when so 0, 0, 1, what are we getting? Difference is 1 and borrowed is 1. What is there here also? It is proved. Then what is here? See, 0, 1, 0. Then what? 0, 1, 0 means difference is 1, borrowed is 1. So same here also. And after that, A, B and B in 0, 1, 1. We were getting difference as 1 and borrowed as 1. Borrowed difference as 1 and borrowed also 1. See here also we get that. And here 1, 0, 0, and the difference is 1 and borrowed is 0. In the same way, we are getting the same output as in the truth table. Hence, implementation of full subtractor in Verilog is done. Thank you.